Science seminars here. Hi, it's Dr. Licker to have with us today one of our own. Again, Deborah Blevins today from across the hall. Yep. To find out if you can hear today. You over there? Yeah, I'm here. So we'd like to welcome you to Science Seminar again this week, brought to you by the Department of Chemistry and Physics here at the University. We're happy to do that. We're happy to have Dr. Blevins with us today. It's always fun to get to know these people a little bit, where they're from, where they're going in life. And Dr. Blevins is from Kentucky, the Cumberland's part of Kentucky. Yes, where she got her Bachelor of Arts in Mathematics at the University of the Cumberlands. Then she got a master's in mathematics from the University of Kentucky. And then she got her PhD in mathematics from, where do you think? Yeah, from Kentucky, University of Kentucky. Yeah, so yeah, she was born and raised, and where do you think? Kentucky. I learned a lot about Kentucky. I'm looking forward to lunch afterwards. Those old Kentucky songs. Yeah. So anyway, I was looking on at Dr. Blevins' page here on the her and she said some nice stuff, and she says in here that math is deep and seemingly unending. And first we do the adding and subtracting, and then you do the multiplication, and do the powers of exponents and algebra and calculus, trigonometry, or the trigonometry first, trigonometry and then calculus. And it's like, yeah, I never end linear algebra, differential equations. And then there's the stuff that Dr. Krause talks about across the hall from me, all these different spaces. It's like, I don't know one space, this space. He talks about all these other spaces, and it's never. And I'm related to sort of God's word is deep and unending. There's always new stuff to learn in mathematics, chemistry, biology, and so also as to study God's word. So I think that's a really thing. And after that, I'm going to take one of her classes next semester. Yes, it's open. Registration is open. My IDs are sending me stuff already, so I'm going to see if I can get it. So I want to remind you that we have lunch after the science seminar, and Dr. Blevins will be with us, and she'll be able to tell you more about her journeys in math, life in general. And I hope you join us for that. We'll be in the Joyce Room of the Corner Cafe. If you do not have a meal plan, if you're visiting or something like that, we will pay for your lunch if you want to join us for lunch today. And let's give Dr. Blevins a warm welcome. Click this on. Put this on you some.
Okay.
All right.
No problem. This is fancy stuff here. Do I have a back pocket? Nope. Okay. Well, thank you all so much for coming. I'm excited to be here today and talk to you a little bit about my mathematical life. So this is maybe a bit of an intimidating title with lots of acronyms. So we'll talk about all of that stuff. Don't worry if that doesn't make sense quite yet. What I'm going to be talking about today is the research that I did actually in the summer of 2019, so it's been a little while now. But I did an internship at Oak Ridge National Laboratory when I was a graduate student at University of Kentucky. And it was a 10-week internship over the summer sponsored by the NSF. There's Mathematical Sciences Graduate Internship Program, I think. Again, more acronyms. There are equivalents for undergrads, so if you have questions, I'm not like the authority on that sort of thing, but I'm happy to tell you about my experience and that sort of thing. It was very formative for me. So I'm going to talk to you a little bit about what I did. I had 2 projects while I was there. I'm going to focus on one of them and then kind of talk to you about how the team took this work and extended it and took it further, and some of the changes that they made after I was gone. So that is the plan. Again, don't worry about this title. We're going to break this down in the next couple of slides. So So the main idea here is we're talking about vehicle security. So I will say that this particular topic is very different from my other mathematical life. So my PhD, my dissertation was all focused on number theory, very algebraic. All of this is very much not that. So it was a huge, talking about math being deep and unending, it was very new. And still, again, this is not really what I do in my mathematical life. But it was a great experience to learn some of these different things that I didn't do regularly. So some CAN basics. CAN stands for Controller Area Network. So the idea is we have a vehicle, and inside this vehicle we have computers called electronic control units. And these computers control the functions of the vehicle, and there's lots of computers, and they're talking to each other, okay? So they broadcast messages using what we call a controller area network bus. We will call that the CAN bus, okay? And these messages that are sent, so you'll see them called messages or frames or packets or something like that. And there's two main parts. The first part is what we call arbitration ID. You will see that abbreviated AID throughout the remainder of the talk. And then we have the data itself. So for example, maybe the message that the computer is sending is that the headlights are on, okay? So that's what's contained in sort of the message piece. It's telling the car, okay, the lights are on. This AID is just a label. It's basically to say, this message is about the headlights, right? And then what am I telling you about the headlights? It's that the headlights are on. It's called arbitration because, as you can imagine, there's lots of messages being sent at the same time. Tons of things that the car needs to know, right? It needs to know the headlights are on, but also needs to know that the car's in drive, and it needs to know if a door is open and all sorts of things. So if two messages come at the same time, then the way that the computers decide which message it's going to listen to is through this arbitration ID. So it's telling the computer something about which one to listen to, and that'll be relevant later on. But you can also think of it as a label, okay? The problem with this system is that it lacks security. So there's no encryption, there's no authentication required to access the CAN bus, this system of computers. There's no information about who's sending and receiving this information, right? That's what we mean when we talk about a broadcast network. And the CAN bus is both remotely accessible and physically accessible via the OBD2 port. So if you don't know what that is, if your car is having an issue, your check engine light comes on, you take it to the mechanic, they're going to plug something into your OBD2 port to read the message that the car is sending to tell them what's wrong, okay? So your mechanic can access the CAN bus, you can access the CAN bus through this OBD2 port, okay? So what this means, right, is this is not particularly secure. And if things are not particularly secure, then we can exploit that, right, to do potentially malicious things. So we would want to detect such a thing, right? If someone is going to access the computer network in my car and attack some vehicle that I'm driving, then I certainly want to know about it. And so the goal for our project was to come up with intrusion detection systems. So when you saw the IDS in the title, that's what that stands for. So we wanted to create intrusion detection systems, okay? And there are multiple ways these can be done, but particularly what we did was timing-based detection. So the idea, these messages that are sent, they're sent regularly and redundantly. So if we go back to that message that the headlights are on, then it's not just you turn the headlights on and the computer hears that once. The computer is going, the headlights are on, the headlights are on, the headlights are on, the headlights are on. It's continuously communicating that information, okay? And they're at regular intervals, right? So it should be about the same amount of time between each message, okay? So the simplest way to sort of attack this system is to inject your own message into the computer, okay? So maybe here you see these blue dots throughout the rest of the talk. These are going to represent the ambient frames, the ones that are actually coming from the car, the correct message that yes, in fact, the headlights are on. Okay, but then we could inject frames, right? And we could tell the car that the headlights are off, right? And if we inject that message fast enough, headlights are off, 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 the computer can't hear the message that it's actually being sent, which is that the headlights are on. Okay, that's the idea. We want to sort of inject so many. Well, that would be the idea if you're malicious. We're not on the malicious side. That would be the idea if you were the malicious person, is you want to send the message so fast, again, that the computer kind of can't hear what's actually happening. Okay, and so that's what we're saying here. Must be sent at least as fast for physical effect. Okay. The thing that's good for us, if we're trying to detect those things, is that we can start measuring the time between frames, the time between messages, know what's normal, so we can detect if something is not normal. And that was our goal. So we model these inter-message arrival times. How much time is there between this ambient frame and this ambient frame? Okay. So we needed to have some normal data set. We needed to train and figure out what is normal, so that then, again, we can identify what's not so normal. And so we took 4 different approaches to detection. I'm going to talk about all of these, so I'm not going to unpack them here or talk about what these words mean, but we had 4 different approaches. The mean inter-message arrival time, a kernel density estimation, fitting a Gaussian or a bell curve, and then what we called the binning method. And so we had these 4 methods, and we wanted to figure out which one is computationally efficient, right? If we are trying to detect a malicious attack, we certainly want to be able to do that as quickly as possible. But also, we want to be accurate, right? So those were the 2 things that we wanted to look at. Okay, so how did we train? We had about 8 minutes of data from driving on the Pellissippi Parkway, which is in Tennessee. And in this case, you're driving the car, but you're trying to do all sorts of different scenarios, right? So you are turning the lights on and then off. And maybe you're rolling down a window and then rolling it back up again, and just trying to get all sorts of different scenarios that would be considered normal, just a normal process, so that we don't flag those things. Okay. And then we had the attack data. So this was collected at the Vehicle Security Lab at the National Transportation Research Center. So they have what's called a dynamometer, and your car sits on this dynamometer, and you can perform these attacks without being on the road, which is a good thing, right? We don't want to actually do this on the road. So this gave us a way to sort of inject these frames to have these malicious attacks and physically verify that they were affecting the vehicle, that the vehicle was experiencing some sort of change from these attacks that we were performing. Okay. In our work, we only looked at 2 different AIDs. Okay. Of course, there could be more, but those were the 2 that we looked at. Okay. So what we did was the frames or messages would be labeled malicious if they were during the time that we were actually performing the attack, and then also the AID under attack. Okay, so it's totally possible if you're having some sort of attack that even if what you're attacking is the headlights, for example, something else in the car is being affected, right? So those AIDs might do strange things too, but we don't want to label those necessarily malicious because those aren't directly being attacked. And then otherwise it's benign. Okay, and so we just kind of collected those 3 attacks, 2 AIDs, but 3 separate attacks. Kind of lumped all that data together, and that's what we did our work on. Okay, so just a few definitions that we'll need as we go through these different techniques, these different intrusion detection systems. Some of you may be familiar with these words, but if you're not, that's why they're here. So a true negative, right, is when we have a non-malicious message that was correctly labeled. A false negative would be when we have a malicious I don't know why I can't say that today. That's not good. I have to say that a lot during this talk. Malicious message that is labeled to not be malicious. False positive, non-malicious, labeled malicious. True positive, malicious message labeled correctly, right? So we want to have lots of true positives and true negatives and minimize our false negatives and false positives, right? That is the goal. Some ways we can measure precision. You'll see that we measured precision for each of our different intrusion detection systems. So that's our probability that a message that is actually labeled malicious is in fact an attack. We measured our recall, which is the probability that a malicious message is correctly labeled. And then we also measured false positive rate. So the percent of non-malicious messages that were incorrectly labeled as malicious. So of course we want precision and recall to be high, and we want false positive rate to be low. Okay, and those were 3 things that we looked at for each intrusion detection system. All right, so let's talk about what those were. So the first one is we took the AID that we were going to put under attack, and we took all of that training data, the normal data, and we said, what's the mean inter-message arrival time? Okay, how much time do we typically expect between messages? Okay, and the idea here is this is pretty straightforward. We can calculate that very, very easily, and then it's very easy to check if a message is coming at that time interval, right? If that's the amount of time between 2 messages. And so what we would do is we found that inter-message arrival time, and we said, okay, we're going to mark things as an attack if at least 3 out of the last 6 inter-message arrival times are less than half the mean. Okay, so a couple of comments here. One, we don't just want to alert if we see one surprising inter-message arrival time, right? Because we said there's this whole idea of arbitration, right? So maybe your message comes at the same time as another message, and this message gets priority, and so the car doesn't hear your message. Okay, that's not a bad thing. That's going to happen. Okay, so we don't want to alert if 1 or 2 things is a little bit thrown off. What we want to alert is when this is repeatedly happening. Okay, so you can see here, right? This is sort of worst case scenario for an attacker, right? They're only getting in 1 malicious message between those ambient frames, okay? And they're probably not going to get it right smack dab in the middle either, right? So that's why we want to look back through the last 6 messages. Uh-oh, I'm losing battery. Okay, well, I don't have a laser. We want to look at the last 6 messages and say, okay, what was the arrival time between those? And sometimes it's going to be less than half the mean. Sometimes, like here, sometimes it's going to be larger than half of the mean. Okay, but that's okay. That's why we say 3 out of the last 6, so that we make sure that we catch those. Okay. One comment I do want to make here that we'll sort of address later, less than half the mean was a little bit of an arbitrary choice. Maybe we should actually be checking for less than 3/4 of the mean or less than 1/4 of the mean. We'll come back to that a little bit later. Also 3 out of the last 6, like I said, we chose that because we know weird things happen, but again, it's a little bit arbitrary. So we knew that going in. Okay. So you see what we call our confusion matrix up here, where we address how many true negatives, true positives, false negatives, false positives that we have. And you see that this was actually pretty good. Okay, we had pretty high precision, pretty high recall, pretty low false positive rate. So this was encouraging. Okay, very, very few false negatives in the grand scheme, pretty few false positives as well. Okay, so this was a good system. But we did want to do more. We wanted to make sure that we weren't oversimplifying things by just strictly looking at the mean. Okay. So the next thing we did was a kernel density estimation. And so the idea here was oftentimes, if we look at a histogram, if we model the inter-message arrival time of a particular AID, it could be bimodal, again, because of that arbitration. Sometimes it gets pushed to the bottom and the computer doesn't hear it. And so we actually get this bimodal data. And so we wanted to make sure, okay, are we accounting for that? Okay. And so that's where we tried to use something called a kernel density estimation. Sort of a very rough explanation of that is we want to create a distribution, right? A probability distribution. And we want to we take each value, we sort of build a little distribution over it, kind of weighted by whatever kernel we choose. And we chose a normal bell curve, a Gaussian curve. And that created something like this. This was for this particular histogram, this was our kernel density estimation. This was our probability distribution. Okay. And so then what we did for each message that came through, we calculated the p-value. So you can see the formal definition here. If you've taken statistics, this is the p-value that you've heard of in statistics. If you have not taken statistics, you can sort of think of this as measuring how extreme something is. So if we get a really small number, we're saying, for the p-value, we're saying that's pretty extreme. We would not, according to this probability distribution here, we would not expect to see that, and that's concerning. Okay, and so we had to choose, okay, what sort of threshold do we want? When do we want to say that's extreme enough that we're going to alert that this is problematic? Okay, and so I'll talk about that process in a second. Once we established what that threshold was, then again, we did a similar thing. So we alerted when the p-values of 3 consecutive inter-message arrival times were below that p-value threshold that we set. Okay. And so the way that we came up with that threshold is with an ROC curve. So that stands for receiver operating characteristic. But the punchline of what that is we plot our false positive rate against our recall, right? We want to minimize our false positive rate. We want to maximize our recall. So we end up choosing that sort of corner point there. I've got it in red. I don't know if you can quite see it, but that little red dot represents the threshold that gave us, again, smallest false positive rate while also maximizing recall. For the KDE, that p-value ended up being 0.005. Remember, that was best case scenario, okay? And these were the results that we got. Okay, significantly worse than our first method, right? Poor precision recall, worse false positive rate. So first of all, that's undesirable. We don't want that. We've already seen that we can do better than that. But this method was also pretty computationally expensive as well. We had to create that KDE. We had to check the p-value of every single message that came in and compare it against our threshold. So again, we don't want that, right? We want this to be a quick process. We want to know pretty quickly if something is going wrong, if there's an attack, okay? So then we thought, well, maybe we're working too hard by using a KDE. Maybe we actually could just use a normal curve. Maybe that's fine. So we decided to try that instead. So we just took our AID, we found the mean, we found the standard deviation, and we fit that Gaussian curve to the set of data. So this top picture here, you can see that's the KDE from the previous slide in orange. And so the blue is what it would look like, again, if we didn't bother with all that KDE stuff and just treated it as a normal curve. And then the second one is just a different AID. Again, the orange is the KDE and the blue is the Gaussian, okay? And so we did a similar process. We said, okay, we need to calculate the p-value of every message, and then we tried to figure out what should that threshold be, what's extreme enough that we should alert. And so we did a similar thing. We used an ROC curve to figure out what that threshold should be. Okay. So prepare yourself. This was horrible. Okay. This was not good. Our best case scenario was a p-value of 0.03, which gave us precision and recall in the 50s. So very clear, this is not what we want, right? This was not the right route to take. So we nixed that pretty quickly. And we moved on to our fourth method. Our fourth method is a little bit different from the first three. And so I'll talk a little bit more about this fourth method, which is what we called the binning method. So instead of looking at probability distributions and things of that nature, which were clearly not working out, what we decided to do instead was to look at certain windows, look at sort of a rolling window, okay, and say, how many messages do we see in this window, okay? So we had to choose a window length. So what we did was we found for each AID, okay, we found the mean inter-message arrival time. So we still needed that. And we multiplied that by 4. Okay. Again, we'll come back to that because that's a little bit of an arbitrary choice. But we chose something. We chose 4. Okay. And we said that's our window length. We called it LAID. Okay. And so you would assume, right, that most of the time you would see 4 messages in that window, right? Because we took the average time between message and multiplied it by 4. So we would expect to see about 4, but we know because of arbitration, it can vary a little bit, okay? And so we calculated several different probabilities. So in our training, we said, okay, how many of those windows do we actually not see the message at all? How many times do we see it once? How many times do we see it twice? And so on until we got to 9, and then we said, okay, just 9 or more, okay? We have to stop somewhere. And then we use that to calculate the probabilities. So P sub I is the probability of seeing iframes in that time interval based upon our training data. Okay. So this is an example of one of the AIDs that we used, and it worked out pretty much what we would expect, right? There was an 80% chance that we saw that AID 4 times, okay? That makes sense. That's consistent with what we thought would happen. Seeing it 3 or 5 times was also relatively common, about 10% of the time. And again, that's not concerning because of arbitration and how the system works. Then we see, once we get to seeing it 6 times or more, that's extremely, extremely uncommon, okay? Same thing for 0, 1, and 2 times. But again, those don't concern us, right? What we're concerned with is a message coming so fast that it overrides what the computer's already doing, okay? So we're not worried about these cases where it's 0, 1, or 2 times, okay? But we are worried about 6, 7, 8, or 9 based upon, or more than 9, right? Based upon this data, okay? So with that in mind, what we decided to do was to alert when the last 6 frames arrived in less than that window of time, that LAID number of seconds, okay? And again, so this time the 6 is not arbitrary, right? Because we got that from the probabilities on the previous slide. We knew that, okay, 6 or more is going to be concerning. Okay? Another thing that was really, really nice about this particular method is that the latency was very, very small, meaning the time between when the attack starts and when we detect the attack was basically a mean inter-message arrival time. And so to give you context, those are like fractions of a second, okay? Very, very small amount of time. So I tried to visually express why this would be true, okay? I'm sad my laser doesn't work, but that's okay. So say we've got these blue ambient frames, right? These are coming from the computer. These are the correct frames. And then we have some malicious frames that start getting injected right here at that red one, okay? So when the first one comes in, we would not actually be able to detect it yet, okay? Because if we look at the last 6 frames, we start with that red one. So 1, 2, 3, 4, 5, 6. We're all the way back here. But the amount of time that took was more than our window length, right? Our window length was 4. We've got 1, 2, 3, 4, plus a little bit, right? So that one's not going to get caught. But the next one will. Okay, if we look at the second red dot, malicious frame, we count 6 frames backwards. 1, 2, 3, 4, 5, 6, right? That's going to get caught because the amount of time is 1, 2, 3, plus a little bit of our intermessage arrival time, okay, which is smaller than the window that we established. Okay, so we don't detect the first one, we do detect the second one, and again, there's not very much time in between those, right? This is, again, worst case scenario for an attacker, okay? They're only getting in 1 frame between those ambient frames. Okay, if there's more, then this is going to be really, really fast detection. Okay, so we like that, right? Again, if we're being attacked, we want to know as soon as possible. Okay, so this one allowed for us to do that. That this was, in fact, our best method. Okay, you can see that the precision and recall did go up even from our first method, which was already pretty good. I'll compare them all in the next slide, but I will tell you that those are better. False positive rate is also better. So all of those moved in the direction that we wanted them to move. Also, a bonus here was that we were actually able to identify where many of our false positives and false negatives were actually coming from. Okay, the false positives in attacks 1 and 2, remember this is all the data lumped together for 3 different attacks. So for the first 2 attacks, those false positives that you see came from the attack interval. It was just a different AID, okay? Which again isn't particularly concerning. It would make sense that if one thing's going wrong, probably something else is affected. Okay, so we still don't want false positives, but at least we could sort of identify their origin, which could help us going forward to make this better. And then again, the other false positives and false negatives did occur for that same AID, the one that we were actually attacking. Okay, whether or not it was in the attack interval was, different, but at least it was the AID that was being under attack. So again, being able to identify that says, okay, there's steps we can take maybe moving forward to make this even better. Okay. Okay, so I told you I was going to compare all of the methods. So remember, method 1 was we just strictly used the mean. 2 and 3 were our distribution methods that were not so good. And then method 4 was our binning method. And so you can see, even though method 1 was good, method 4 was even better. Okay. Also faster, very, very fast. Okay, because it was this rolling window, you're looking at the last 6 frames, but you already have the data for the last 5. Okay, so you're just picking up sort of one thing at a time. And then method 1, again, it was still a good one. It was still pretty fast, and it's very straightforward, which a straightforward method certainly has its own advantages. So that was a good thing too. But method 4 was the one that we stuck with. We said, okay, this one is clearly the front runner. So this is really where things left off when I left. I was only in Oak Ridge for 10 weeks. This project, the goal was to actually create a physical object that you can plug into a car's OBD2 port, a vehicle's OBD2 port, and detect malicious attacks. So we had a clear front runner. We knew kind of where we wanted to go with it, but there was more work to be done. As I mentioned, a couple of choices we made were sort of arbitrary. Need to address those things, need to streamline things, and then actually get, again, a physical object that can do the thing that we're trying to do. Okay. So here's sort of what my team changed after I was gone. So first, you'll remember that earlier in the talk, I said the training data that we used came from the Pellissippi Parkway, so actually driving on an actual road. Okay. They actually decided to only use training data from the dynamometer because that's where the attacks took place. So that's just, again, to not throw additional variables into our data. So training data, you do normal things on the dynamometer, train it on normal scenarios, attack on the dynamometer, we keep that variable the same, okay? They also removed outliers in the data. Interestingly enough, it actually worsened the performance of the binning method, the method number 4 that was the best. It did improve the others, not enough that it really mattered, okay? The KDE and the Gaussian were bad enough, okay? It didn't really help them enough for us to care, but it did improve them a little bit, okay? And it didn't worsen the performance of the binning method so drastically that we would say it's no longer the best method, okay? But that was just a thing to note. So then they did create a threshold determination method for all 4 methods. So if you remember, I talked about that ROC curve for the 2 distribution methods, for the KDE and the Gaussian. And we had the ROC curve, and we picked the best threshold there. They also created a process for method 1 and for method 4. So what they did, I won't go into all the details for method 1 because method 4 is the one we ended up going with, but they did find for method 1 that actually they kept the 3 out of 6, but instead of looking at the arrival times being less than half of the mean, it turned out the best case scenario was less than 0.44 of the mean. Okay, so we were actually decently close with our first try at half of the mean, but 0.44 ended up being the best one. So that was the threshold that they would have used if that was the intrusion detection system that they put on the physical detector. Like I said, I'll talk about the next one on the next slide, the method 4. Okay. Also, when they were testing to find these thresholds for the different methods, instead of using that ROC curve that I showed you, they used a precision recall curve instead. So measuring precision on one axis, recall on the other. Of course, those are both things that you want to maximize. So you're looking at that sort of top right point instead of top left. But you can also look at the area under the precision recall curve. So that's what the AUC stands for, area under curve for precision recall. And that's kind of like one value that will say how good this method is. And that precision recall curve actually just works better for imbalanced data. So since some of our data was training and some of it was attack data, they decided that this would be give us better results, better insight into the situation. So they replaced it with precision recall. About 3.9% of our data was attack data, if you're curious. Okay, so for the binning method, they wanted to determine a threshold, right? Does that window length actually need to be 4 times the intermessage arrival time, or should it be some other number, right? We chose 4 kind of arbitrarily. So they looked at 18 different possibilities. They went with 18 simply because we had used 18 different options for methods 2 and 3, and so they just wanted to keep that consistent. So they looked at how the system would run from as small as 1.5 times mu being that window length, all the way up to 10 times mu being the window length. And it turned out that we need 3.5 times our window length. Okay, again, pretty cool that it ends up pretty close to that arbitrary first choice. The 4 was suggested by my mentor, so I probably shouldn't call it arbitrary. He's got a lot of knowledge, and so there was probably some sort of motivation there. But we hadn't mathematically tested it until this point. So the 3.5 was what we chose. I won't talk about how this is the particular latency with that alpha. Changing that does change the latency a little bit. It makes it 3 times that intermessage arrival time plus your computation time. But again, very, very fast, right? These are fractions of a second. So multiplying by 3 is not not doing us too much damage there. And this guy, you can see the precision and the recall up there. They also measured the F1 score, which is sort of a way to combine precision and recall if you're not familiar, and that was about 99%. So all of this was an improvement. It was very, very good. And so they felt confident that they could take this and put it onto a actual plugin prototype. And so they developed this plugin. And I've got 2 YouTube videos that demonstrate this. I'm going to show you the first one, but the reason I have a second one is because you know how YouTube does those suggested videos? It suggests it right at the point where the exciting thing is happening in the video, and it covers it up. So I'm going to give you the heads up now. You can sort of see what's happening, and then I'll show you the second one, which does not have that issue. Okay. I'm not sure if there's going to be sound or not. There is sound on the videos. If there's not, I'll do my best to narrate it, although I will not do as well as my teammate Sam, who did it originally. Find my mouse here. Just listen closely.
Currently go training mode, see what the flashing green light is. The training solid. Bottom device is aerial device, so it will actually eject the attack. Attack today is simply going to change on the button. So I'm going to press this button, eject the bit rate.
You can very briefly see it turn red. Okay, conveniently, that I'm sure that's interesting, but we don't have time for that. Let me pull up the other one for you all. The little pop-up that shows up is actually the next one I'm going to show you. So.
This one idea for to simulate and many actions and stuff. Safety reasons involved down window. Once the training phase is complete, you slide to the vehicle and detect. And the detect phase works by monitoring symbol and as long as you're an adversarial device on this truck, you can send a signal tunnel. Other detectors will notice when spikes. That's we have successful attack.
Okay, it's kind of hard to see with the lighting, but it did turn red if you're paying really, really close attention when the attack started. So this is pretty cool. This is a physical implementation of our intrusion detection system. Also, I'll give a shout out. This is my mentor from Oak Ridge. I should have shouted him out earlier. It's Robert Bridges. Him and Mickey Verma were super crucial to everything that I did at Oak Ridge. So shout out to them. All right, that's it. That's what I've got for you all. Well, if you have any questions, let me know. Here's our lovely list of all the things we needed to do this work. That's a good question. So I guess who's doing them would do. I should say there's a lot of different ways that you could potentially attack a vehicle. We just looked at one that sort of exploits the timing. So also I should preface, I can't say a ton of stuff because it's from a national lab. So probably what I can say is that some of these papers talk a little bit more about who's doing it and what they could be doing and why it's dangerous. But I guess one example, the example that you saw in the video was dealing with like the coolant temperature. And so it could be telling your vehicle like you're overheating, it's way, way, way too hot, which as you saw kind of caused the car to freak out and shut down and just not do anything at that point. So things like that, that's an example of something that could be done. My personal understanding is that the general public is not in danger of this, of being attacked, but there are parties that might be interested, parties that might be concerned. As I said, I can't say too much because it's government, technically, government work, so. I think you would have, my understanding is that you would have to send it more frequently, simply because if you send it at the same frequency, things could happen with like arbitration. Your message might not get heard, right? The computer might listen to a different message. Essentially, you want to send them so fast that it sort of overrides the ambient messages. But you would, if you're going to do this, like I guess you're, it would be helpful to know that interval that the messages are typically transmitted. Yeah.
So you were doing this as an internship.
Mhm. I got my master's. I was working on the PhD. Yeah. Mm-hmm.
What they were doing, seeing math abilities, or what you learned from learning more about this. What was your experience takeaway?
I would say it was definitely more on the side of I was learning from them. So most of this was coding in Python, and I had about this much knowledge about Python. I knew more than zero, which is why I got the job. But when I got there, they were like, this is not much more than zero. So that was a big hurdle for me. I think I could have done a lot more, a lot faster, and maybe used some of my mathematical knowledge if I hadn't had the hurdle of Python. But even so, where it was so different from the math that I do normally, it was much more a learning from them type process, for sure. Yeah.
When there was all vote access.
Hmm.
So I would assume going to be the means by which attacks are, what type of vote access are you talking about?
That I don't understand as well. All the like hardware type stuff, I know remote stuff. Anyway, you'd have to have hardware to do it. Is not really my field of expertise. So I don't know. I know that it's possible to do it remotely, but I don't really know what it looks like. I do know in that second video, you might have heard him say, and it was a little bit hard to hear, that there was a device hidden in the vehicle. So that wouldn't be remote, but it would be less obvious than just, sticking something in the OBD2 port. So there could be other ways to attack that are maybe less obvious. But like I said, I don't know the details on the remote attacks. No, at this point, it would just be, again, I don't know if they've done more beyond that point. I think that video was from 2021. So it's very possible that they have taken it even further. But at that point, the goal was just, we want to detect it. We want to alert the driver that something's going on. Yeah.
A few years ago, there was this big
Model signals.
I suppose it's possible. I don't know.
Question. We'll be up here for a few minutes, and we'll also be meeting together in the Joyce Room of the Corner Cafe. So please join us there. Next week, we have a talk on biology and some gene modification and stuff like that. So a whole different things to discuss the next time. Let's thank our speaker one more time. Gotta be. He